Hello, everyone. Welcome back. Today, I want to talk about vector operations, so specific operations with vectors. These are not going to be all vector operations, but some of the ones that are useful for us right now. So, a few things we want to be able to do, our goals, be able to write a vector component form. We'll explain that. Okay, be able to find the magnitude of a vector, the length of a vector. Also, be able to add vectors. How to do that, not only in component form, but also be able to multiply vectors and a certain type of vector multiplication, and then also be to find the angle between vectors, a direction angle, and also the angle between vectors. Okay, so first, let's take a look at vector components. And a good way to think about this is graphically. So let's say we have a vector that has its tail at the origin. Let's just do one in the first quadrant to make life easier. Okay, and let's say the head of the vector can end at the point, let's say 5, 4. Okay, let's call this vector u. You call it whatever you want. Okay, then a couple ways we can write that. We can say that u is equal to, and we use these special kind of brackets, these kind of triangular shaped brackets, 5, 4, where this we say 5 is the what's called x component, the component in the x direction along the x-axis, and 4 is the component along the y-axis. Now, a vector can be in any quadrant, so these numbers can be negative, positive, or 0. That just shows the basic convention. Okay, that's one way to do vector components. Another way is with what are called unit vectors, and we'll explain unit vectors a bit more later. But we can also write u like this, where we'd have 5 times I, and once again, I itself is a vector, plus 4 times j. Okay, and what I and j are, let me explain those below here. Okay, if we have a vector, in fact, let me actually change colors here. It makes it a little bit easier. So if we have a vector right here, okay, where it starts at the origin and it ends at 1, 0, this is the vector I. Okay, so the vector I is itself a vector with components 1 and x component 1 and y component 0. And then we have another vector, similarly, where this endpoint is 0, 1, and that's what they call the vector j, and it has components 0, 1. So basically, these are called unit vectors. And so basically, we have a unit vector in the x direction and a unit vector in the y direction. So we can always write a vector in 2 dimensions in terms of writing what's called a linear combination of those 2 vectors. Now, we also do things that we won't look at here. We also do vectors in 3 dimensions, so it actually add another component vector, z. Okay, so that's the idea of component vector. All right, so we can write any vector component form, basically going from, if its tail is at the origin, then where the head ends, what point that ends on, gives us our components. Now, let's find the magnitude of a few vectors. Okay, so let's say we have, and let's say here we're going to have vectors that end at a certain point. Let's say we have 2 points in space. All right, so one point is going to be 2, -3. Let's call this point K. Another point is going to be 4, 0. Let's call this point L. And so we have a vector that goes from here to there, and that vector, we're going to call that just simply KL. Remember, it indicates a vector, put a line over it. So we want to find the magnitude, okay, 1 of this vector KL. Basically, how we do that then is essentially the same as the distance formula. So if you remember the distance formula from algebra, same thing. Okay, and so we can do that. And so and when we write the magnitude is with the absolute value bars. So the magnitude of KL is going to be, and since using the distance formula, and that's going to be the difference in our x's. So 2 minus 4. squared plus the difference in our y's, negative 3 plus or minus 0 squared. Okay, and so that's going to be the square root of, that's going to be negative 2 squared plus negative 3 squared. So I can squeeze this in here. And so that's going to be square root of 4 plus 9. And so that's going to be the square root of 13. Okay, so the magnitude of that vector, in this case, the one we drew from, was the tail at this point 2, negative 3, and ahead at 4, 0, is just simply going to be the square root of 13. That's its length. That's its magnitude. Okay. Now, what if we have another vector? In this case, number 2, let's say of a vector we're going to simply call, let's call a vector v. And let's say this vector is, instead of this way written this way, it's actually going to be written like, say, but we have negative 7 and 2. Oops, make sure you use the right brackets. So this is our vector in component form, which also can be written as negative 7 times I plus 2 times j, either way. Think about this. And this time, we're just saying essentially it starts at the origin, as its tail at the origin, and then from negative 7, 2 is about right here. So it points in this direction. Okay. So here we also essentially use the distance formula, but here's the simpler case when the tail is the origin. So the magnitude of v is going to be the square root of negative 7 squared plus 2 squared. And so that's going to be negative 7 squared is 49 plus 2 is 4. And so that's going to be the square root of 53, which we can't simplify. But that's the magnitude of that vector's length. It's 53, the square root of 53. Okay. So depending on what kind of situation we're given, we can easily find the magnitude of the vector. Okay. Now, let's also talk about a couple of different ideas. We're called scalar multiplication and then vector addition. All right. Now, scalar multiplication, there are two ways we can multiply a vector. We'll see two ways for first. These just want to talk about what's called scalar multiplication. Remember, scalar is a number we can describe by just one number, like magnitude. Or vector, we have to describe by two numbers, at least in 2 dimensions, basically using direction and magnitude. In 2 dimensions, we can also describe it in component form as components x and y. Okay. What's called scalar multiplication, we can multiply that. Essentially, we multiply each component by that vector. Okay. And so if I look at this, scalar multiplication. Okay. Let's say I have a scalar. Let's say I have a scalar. Well, let's do another vector. I'll probably use the same one I did. So let's use vector v. Okay, which is equal to negative 7, 2. Okay, and let's say what I want is 2 times v. Okay, and what that is, that's going to be 2 times v in component form, negative 7, 2. So what I do then is I simply multiply 2 times each component. So 2 times negative 7 is my new x component in the x direction along the x-axis. Then 2 times 2 is my new component along the y-axis. And so the vector 2v is just going to be negative 14 and 4. Okay. Now, what's interesting, if you do this, I won't show it, you can try this on your own. But actually what this would do is make as a vector, so 2v, okay, is the same direction as vector v, the one we had before, but twice as long. Okay, so if I do the magnitude of 2v is basically 2 times the magnitude of v, what I found a moment ago. So this is going to be 2 times the square root of 53. You can try that on your own and find out. Let's find the magnitude of this vector, but you'll see it's twice that. Okay, that's what's called scalar multiplication. Now, let's talk about vector addition. And basically here I'm also including subtraction as well, because you could have, if you remember, subtraction is simply adding a negative. So let's do a couple new vectors. Let's say u is going to be the vector 1, 3, 1, 4. That's fine. And v is going to be the vector -2, -1. Okay. So what this says, if I want to add vectors, I add the components. I add the corresponding components, the y components together and the x components together. So u plus v is simply going to be a new vector, and its components are going to be 1 plus a -2. Its x components will be the sum of the x components of the original two vectors. And the y component will be the sum of the components of the original two y components. So 4 plus a -1. And so that's going to be 1 and -2 is -1. 4 and -1 is going to be 3. And so that's the sum then in components of that new vector. So if we graph that, so u is 1 and 4. Okay. And v was -2, -1. About right here. Then u plus v is -1, 3, so about right here. And if you remember if you watched my previous video on how we actually add vectors graphically, notice that should be about approximately where it is. Okay, so this is the vector u plus v. Okay. Now, so we can also combine scalar multiplication with vector addition. So we can also multiply u and v times any scalar we want, and then combine them that way. They're adding or subtracting. We can do that as well. Okay. Now let's return to the idea of a unit vector. So, as we said, let's take our vector u, 1, 4, and we said it could be written also as 1 times unit vector I plus 4 times unit vector j. Okay. Actually, give me just a moment. Let's see if I actually want to do this right now. Let me think just a second. So I apologize. Give me just a moment here. Okay. Let's show that this is also true. Okay. So I, we said, was equal to unit vector I was 1, 0. Unit vector j was 0, 1. Okay. I can actually show and get the same thing. So if I do u plus I, then that's going to be sorry, hang on just a second. Okay. Actually, I apologize. Let me change this. I'm thinking about doing something, but I think it's maybe too confusing right here. So let me just skip that and think about it later. We need to come back to that later. We can. All right. Let's take a look. So that is how we do then vector addition. Of course, if you want to subtract, you just subtract the vector, right? And you're just essentially the same as adding a negative. Okay. Now, let's see what's next. All right, so another way to multiply vectors or vector multiplication is what's called the dot product. Okay, let's talk about that. So let's take a look over here where it says multiplication. It's called the dot product. And what we're going to do then, let's take the same vectors we had. So u and so 1, 4, -2, -1. Okay. So u is equal to the vector 1, 4. And v is equal to the vector -4. Sorry, -2, -1, rather. Okay, so we have what's called the dot product. This is the way we can multiply the vectors. So the dot product, as this says, what we do is to multiply u times v, we just multiply the x components together plus the y components together. This result is actually a scalar. So we're actually going from a vector to a scalar. So in this case, u dot v, okay, is simply going to be 1 times -2, the x components multiplied together, plus 4 times -1, the y components multiply together, and this is going to be -2 minus 4, and this is equal to -6. Once again, this is a scalar. This is no longer a vector. Okay? So this is a different kind of vector multiplication, where once again, what's called a dot product. Okay? Now, what is the dot product used for? Well, imagine you have imagine we have like a pipe or something like that here. All right. And imagine we have, some fluid flow in this direction. So fluid flow would say would have magnitude and direction. Okay. And now we also have what's called if we have a vector that points out in this direction. Okay. Let's say the fluid flow vector is called F. Okay. Magnitude direction. This is what's called a normal vector. And basically means it's perpendicular to the surface. That's what it means normal. Okay. So what we'd say then is basically this kind of gives us an idea of how much of this fluid, kind of what fraction of this fluid will actually enter the pipe. If it's not coming in a straight line, either in or out, this will actually tell us then, give us some idea of whether fluid's flowing in or out, and then also what magnitude. Okay. So it turns out then the flow into the pipe is basically F dot N in magnitude. So that's the magnitude essentially that flows in the pipe tells us that. Okay. Now, what's interesting about this, as you can imagine, and we'll see in a relationship here in a minute, relates this dot product to the cosine of this angle between the vectors. Basically, if these vectors are straight in a line, all the fluid essentially flowing, or as much fluid as possible, is flowing into the pipe or out of the pipe. But if my flow is perpendicular to the pipe, okay, going in this direction up or down, essentially no fluid goes in at all. Okay, and that's actually the cosine. That's where this comes from, why this is useful. So basically, to do a dot product, then we essentially multiply those together. Okay, excuse me just a moment, I need to pause the recording. Okay, I'm back. So a couple more things I want to discuss. So let's talk about the direction angle of the vectors. We'll just take one of the vectors we have. Let's do a simple one, just 1, 4. Actually, let's take -2, -1. Okay, so direction angle. Okay, so our vector v we said was -2, -1. Let's use the same vector, so -2, -1. we draw a picture, of course, that's going to be in this quadrant. So -2, -1 is maybe about right here. All right, what we want then is a direction angle basically from the positive x-axis, which you're considering to be 0 degrees. So it's 270. Okay. Now, what we're going to do, let me actually enlarge this a bit. So in this quadrant, quadrant 3, so what we have then are basically these lengths. So this, of course, is -2. This is -1. So what we want to find then is this theta. This is basically a reference angle. Okay. And we have this relationship. So the tangent of theta, we're going to see essentially just the absolute value of y over x. The reason we use the absolute value is always have a positive value, then depending on which quadrant you're in. Remember, reference angle is always used with respect to the x-axis. Okay, so in this case, tangent of theta is going to be y over x, which I have the absolute value of that. So -2 over negative, sorry, the other way around, -1 over -2. Of course, that's going to be the tangent of theta is equal to +1/2. And then theta, if we take the inverse tangent of both sides, get the theta is equal to the inverse tangent of 1/2. Okay, make sure we're in degree mode on your calculators. And let's actually going to go to Desmos. Get rid of that stray mark. Okay, so go to Desmos. Make sure we're in degree mode. Switch to degree mode. Then the inverse trig function. You go to functions and go to inverse tangent, then 1/2. And the two places, that's approximately 26.57 degrees. Okay. So 26.57 degrees. So what we want then is actually this angle right here. Okay. This is our direction angle. I should probably call it something. Let me call it alpha. Okay. And so we know, if you understand reference angles, basically the image. So once again, this is of course 180 degrees right here. So we need to find, just basically add this to 180. So our direction angle is equal to alpha is equal to 180 plus that in this case. So we know which quadrant we're in. And basically which quadrant we're in depends on whether you, what you do with that reference angle. 180 plus 26.57 degrees. And so that, of course, is going to be 106.57 degrees. So that's our direction angle. So that's the angle with respect to 0 degrees here on the x-axis. So that tells us what direction it points in then based on, once again, as using 0 degrees as our positive x-axis. Okay. Now, we can also find the angle between vectors. So let's go back to our vectors we had just a minute ago. We use the same ones. So u and v. So v is -2, -1. U is 1 and 4. Okay. So 1 and 4. So vector u is about right here. So this is 1 and 4. And this is -2, -1. So it's about right here. This is vector v. So one of the angle between these vectors, let's call that in this case theta. Okay. So our formula says this. If you look over here, says that the cosine of theta is equal to u dot v, the dot product, divided by the magnitude of both vectors. So what you need to do then is find the magnitude of both vectors. We already know the dot product. We found that before. So u dot v from our previous example is -6. Okay. And the magnitude of u is going to be then essentially the Pythagorean theorem. So the square root of 1 squared plus 4 squared. And that's going to be basically 1 plus 16, which is 17. Okay. Then the magnitude of V is going to be the square root of -1 squared plus -2 squared. And so that's going to be 1 plus 4, and that's going to be the square root of 5. Okay, so cosine of this angle between them, theta, is equal to -6, which is u dot v, divided by the square root of 17 times the square root of 5. We can do that on Desmos. So let's do that. Okay, so -6 divided by, to do a square root, just type SQRT, 17, an arrow to get back in front of the square root, times SQRT of 5. And so that value is about, let's use about 5 places, -0.65079, -0.6, and they were about 65079. Now, of course, if you take the inverse cosine of both sides, and theta is equal to the inverse cosine of that. Okay, let's find out what that is. And that will tell us the angle between those two vectors. So once again, go to functions, inverse cosine, and then do that again. So we're supposed to put on the next line. Inverse cosine of -0.65079. And that's, as you can see, approximately 2 places 130.60. So 130.60 degrees. Okay, far so we'll also make sure it looks reasonable, and based on our picture, those look fairly reasonable. That'd be the angle in between those vectors. Okay, one more thing from this formula, we can see our formula over here. What we can say then also is that u dot v is also equal to the magnitude, the product, or the multiplication of both vectors, the magnitudes of both vectors, okay, times the cosine of theta. Okay, so remember, if theta is 90 degrees, cosine is 0, and that's what we set up here in our explanation of what kind of how the dot product is useful. Is basically, instead of our flow is going perpendicular to the entrance of our pipe, since you're going up or down in this example, basically there should be no flow into it. And the angle between those two vectors, between F and N, would be 90 degrees. The cosine would be 0, basically there'd be no flow inside of it. Okay, but if the base of the fluid flow, so basically if the fluid flow is going in to the pipe, then of course these would be in the same, be parallel, but in opposite directions. The fluid's going out of the pipe, and so your dot product would be negative in that case, since going into the out of the pipe would be positive. Okay, so what we learned today are some basic vector operations. We learned how to write vectors in component form, how to find their magnitudes, able to add and subtract vectors, multiplication, multiply vectors using the dot product. Also talk about the angle between vectors and the direction angle. Thank you. Have a good day.